Hello, and welcome to this next presentation in the analysis of circular motion. In previous presentations, we've considered D'Alembert's principle and the use of inertial forces related to fixed body axes, and how using this principle we can consider a dynamic situation such as a rotating mass as a static analysis. And we know from previous presentations that centrifugal force is actually an inertial force. We proved previously that for a circular motion, the only force actually required is the centripetal force, the inward seeking force, shown here. The hammer thrower must apply this centripetal force to the hammer. For Newton's third law, there must be an equal and opposite reaction to the centripetal force, and using D'Alembert's principle, we would call that the centrifugal force, a force that can be considered to act outwards. So in other words, with the D'Alembert's analysis, the centripetal force acts on the body to cause the circular motion. The centrifugal force is a reaction from the body due to its inertia and its inbuilt resistance to change in motion. So as we've outlined previously, centrifugal force is simply a concept, but it's a concept that engineers find very useful in analysing dynamic situations. And from the hammer thrower's perspective, when rotating the hammer, it certainly feels like there is an outward force, a centrifugal force. But this again is purely due to the fact that the hammer is subject to a change in motion, and the inertia effect opposing this change in motion gives the perception of an outward force. So in this presentation, we're purely going to consider applications of centrifugal force and how to analyse various problems involving circular motion.
Here's a brief overview of the underpinning knowledge required for this presentation. Having reviewed the previous presentation related to angular motion and the angular motion equations derived, being aware of Newton's laws of motion, being aware of D'Alembert's principle, in this presentation the use of centrifugal force, understanding what's termed the equilibrium conditions, for example upwards forces equals to downwards forces, and forces to the right must equal forces to the left, and also the conversion from revs per minute into radians per second, multiplying by 2 pi upon 60. In latter questions of the presentation, we will also need to construct free body diagrams of our various rotating masses. In some questions we will need to calculate the weight force. Remember, weight force is equal to mass multiplied by gravitational acceleration. The next few slides relate to a recap of the previous lecture, and the questions, which is the main purpose of this presentation, commence around 7 minutes into the presentation.
Here's a very brief overview of centripetal acceleration and centripetal force. We derived centripetal acceleration in our previous presentation and also centripetal force. If a mass m, shown here, located at the end of a piece of cord of length r, shown here, if the mass is rotated at a constant angular velocity, omega, shown here, in a circular path about center O, shown here, then for this circular motion, the mass m is constantly changing its direction. So we mean by that, initially the velocity vector is shown here, at this instance, and then some angle theta later, the mass is moved to here, and now this is the linear velocity at this point. Remember that velocity is a vector property, so it not only has a magnitude but a direction. So though the magnitude of v is the same here and here, the direction is different. And if there's a change in direction, there must have been an acceleration in the system. So for Newton's first law, for a change of direction to occur, an external force must be applied to the mass. For circular motion, as we outlined in the previous presentation, this force is termed the centripetal force and can be shown to be directed inwards towards the center of rotation, O. From Newton's second law, if the force is applied, an acceleration is produced. And here's Newton's second law stated for reference, F equals ma. So here are the formulae related to centripetal acceleration and centripetal force we derived in our previous presentation. I'm just listing them here for ease of reference. So we know that Newton's second law is defined as F equals ma. For circular motion, the inward acceleration, termed the centripetal acceleration, was derived as A is equal to omega squared r, unit meters per second squared, and this formula is in terms of angular velocity omega, shown here. Again, from a previous presentation, we derived the relationship between angular velocity omega and linear velocity v. Omega is v divided by r. So now replacing omega with v divided by r, we can also show that centripetal acceleration A is equal to v squared divided by r. A is still in meters per second squared, but now the relationship is in terms of linear velocity. So now if we return to Newton's second law shown above, and this time replace the A in the equation, we can derive an equation for centripetal force, F, is m omega squared r. This is a force, so the unit is a Newton, in terms of angular velocity omega. And finally, replacing A this time with the v squared upon r, we can also show that centripetal force F is equal to mv squared upon r. Still the unit is a Newton, but now in terms of linear velocity. So those were the equations that we derived in our previous presentation, and I just stated here for reference. As to whether we use the formula related to angular velocity or linear velocity depends on the information given in the question. So here are the first three questions from our worksheet. In question 1, a point on a wheel's rim of 1.32 meters diameter is moving with a tangential, that's the linear, velocity of 3 meters per second. We've got to calculate the magnitude and direction of the centripetal acceleration at this point. Answer is given here in the bracket. So that's a kinematic problem. Question 2, the tip of a turbine blade has a radius of 576 millimeters. This tip here, for example. If the blade rotates at 3000 revs per minute, we've got to calculate the centripetal acceleration on the tip of the blade. Again, centripetal acceleration out here. That's a linear acceleration shown in the bracket here. And question 3, we've got to find the centripetal force this time required to keep a mass of 5 kilograms moving in a horizontal circular path of 3 meters diameter and at a uniform speed of 150 revs per minute. They will no doubt make the assumption that weight is ignored in that particular question. This is a dynamic problem. This time we're calculating the force required. I would encourage you to start the presentation and attempt these questions using the equations from the previous slide. The equations shown here for reference. But I will show you the full work solutions on the following slides. So question 1 solution, we're trying to find the magnitude and direction of the centripetal acceleration in this case. We're given in the question the diameter of the wheel, so capital D shown here. The radius is obviously half the diameter, and we're given the tangential or linear velocity, the 3 meters per second, that's v shown here. To calculate the centripetal acceleration, I'm using the equation A is equal to v squared divided by r from our previous slide. Inserting the values, the linear acceleration is 13.6 meters per second squared, and the direction of the acceleration is, of course, inwards. Question 2, solution. Here we have to calculate the centripetal acceleration of the tip of a blade. So for example, this tip of this blade here. Again, in the question, we're given the radius of the blade. It's 576 millimeters. Note that I've converted that immediately into meters, 0.576 meters. Must always use meters in these calculations. And next I've calculated the angular velocity omega. We're given 3000 revs per minute in the question is the angular velocity, so my conversion is 3000 revs per minute multiplied by 2 pi upon 60. So 314 radians per second is the angular velocity. Again, we're asked to calculate the centripetal acceleration. So this time I'm using the formula A is equal to omega squared r, certain the values from above. The centripetal acceleration is 56,850 meters per second squared, and of course the direction of the acceleration is again inwards.
And just note for reference, the 314 radians per second could have been stated more accurately as 100 pi radians per second. It'll make very little difference to the final answer, but the 100 pi radians is the exact value for omega.
Question 3 solution. We've got to find this time the centripetal force necessary to keep a mass 5 kilograms, moving in a circular path of diameter 3 meters, so d is 3 meters, and of course the radius of rotation here is 1.5 meters, and we're given the uniform speed 150 revs per minute. So again, my angular velocity 150 rpm multiplied by 2 pi upon 60, so that's 15.71 radians per second for the angular velocity used in the calculations. This time we're calculating the centripetal force, so given the information in the question, the angular velocity, I'm using the formula for centripetal force is F equals m omega squared r. Inserting the values from above, the force is 1.85 kilonewtons or 1,850 newtons, and of course the direction of the centripetal force is inwards.
And again, notice we could have written the 15.71 radians per second more accurately as 5 pi radians per second, just for reference.
Here's the next batch of questions. Question 4. We have a mass of 10 kilograms is supported on a light rigid rod of negligible mass. It's a rigid rod, so it doesn't extend, and it's light, so we don't need to worry about its mass. And this mass is rotating at a radius of 20 centimeters in a horizontal plane at an angular velocity of 2.5 revs per second. We've got to calculate the centripetal force acting on the mass. There's a hint in the question here that the angular velocity is actually stated in revs per second, not revs per minute, so just be careful with that. The answer for the centripetal force is shown in the bracket here. Question 5. The maximum safe tension of a cord is 0.5 kilonewtons. That's actually going to be the maximum centripetal force that we can apply to the cord. We're asked to calculate the greatest mass which can be attached to a 700 millimeter length of cord and rotated in a horizontal circle with a tangential velocity, linear velocity of 12 meters per second. Requires some transposition in this particular question, and the maximum mass we can have given the constraints is 2.43 kilograms. Question 6. A mass of 2 kilograms is whirled around on a smooth horizontal surface on the end of a 1.2 centimeter long string. The other end of the string is considered fixed. If the string breaks under a pull of 50 newtons, that's the maximum centripetal force we can apply to the string, we've got to determine the maximum speed of rotation in revolutions per minute, which is shown in the bracket here. Again, some transposition required there. I would encourage you to stop the presentation and attempt these questions, but the full work solutions are shown on the following slides. Question 4, solution. We're asked to calculate the centripetal force acting on the mass. We're given in the question the mass of the body, it's 10 kilograms, so m is 10 kilograms. The mass rotates at a radius of 20 centimeters, so r is 20 centimeters. Notice converted that straight away into meters, 0.2 meters. and it rotates in a horizontal plane at 2.5 revs per second. Just be careful here calculating the angular velocity. It's 2.5 revolutions per second, and we just multiply that by 2 pi. We're just converting the revolutions into radians here. The time is already in terms of seconds. So that's 15.71 radians per second. To calculate the centripetal force, F is equal to m omega squared r, inserting the values. That's 493 newtons, and of course the direction of the force is inwards. Here's question 5, solution. This time we're asked to calculate the greatest mass that can be attached to a piece of cord in this particular situation. So the question states the maximum safe tension for the cord, 0.5 kilonewtons. That's effectively the maximum centripetal force we can apply, F. So 0.5 kilonewtons, that's 500 newtons. We're given the length of the cord, the radius of rotation in this case. So R is equal to 700 millimeters or 0.7 meters. And we're also given the tangential velocity, 12 meters per second. So that's really linear velocity V, 12 meters per second. Now in this particular case, we've got to determine the magnitude of the mass, so we're going to have to transpose the equation. I'm using the centripetal force equation, F equals mv squared divided by r, because I'm actually given v in the question. So to rearrange the equation, I simply multiply both sides of the equation by r and divide both sides by v squared. So m is equal to F multiplied by r divided by v squared. Inserting the values, the maximum mass we can have is 2.43 kilograms. And question 6, solution. This particular problem, we've got to determine the maximum speed of rotation in revs per minute. So in the question, we're given the mass of 2 kilograms, so m is 2 kilograms. We're given the radius of rotation, the string length, in other words, is r is 120 centimeters, so 1.2 meters. And we're given the breaking strength of the string that occurs at 50 newtons. So that's basically the centripetal force of 50 newtons. This time we've got to find the speed of rotation. So I'm going to use the formula for centripetal force, F equals m omega squared r this time, because I need to find omega. So rearranging the equation, dividing both sides by mr, omega squared is equal to F divided by mr. And of course, to find omega, we simply square root both sides, so square root of F divided by mr. Inserting the values and evaluating, that's 4.564 radians per second, but don't forget the answer in the question is stated in terms of revs per minute. So to find the answer in terms of revs per minute, it's 4.564 multiplied by 60 divided by 2 pi, so 43.6 RPM. So here's our next batch of questions. Question 7. A mass of 60 grams is required to balance a motor car wheel. The mass is attached to a 0.33 meter diameter rim. We've got to calculate the centrifugal force acting on the rim when the wheel is rotating at 470 revs per minute. Force is shown in the bracket here. Question 8. Slightly more thought-provoking question. An object has a mass of 3,000 grams. It's attached to the end of a rod and it's whirled around in a vertical circle of 1 meter radius. We're asked to calculate the maximum minimum tensions induced in the rod when the object achieves 180 RPM. An assumption made here is that the extension of the rod is deemed negligible, so the rod doesn't change its length. So this is slightly more complicated problem. It's actually in 2 parts. We need to consider a maximum and minimum tensions. If you think of this object being rotated in a vertical circle, we'll actually have the minimum tension in the rod when the object is at the top of the travel, maximum height, and it will have the maximum tension in the rod when the object is at its lowest height. What you need to do is consider the 2 separate situations. First of all, draw a free body diagram of the mass at the top of the motion of the circle, what are the forces acting in a particular case, and evaluate the tension in the rod, and then consider the object at the lowest point of travel, and again draw a free body diagram of all the forces acting, and then again calculate the force in the rod.
Question 8 is a hint Here are the two scenarios. A shown here, where the mass m is at the lowest point of travel, and scenario B, where mass m is at its highest point of travel. In each case, we need to consider the free body diagram of the mass at the bottom and at the top, and consider all the forces acting on the body. Note that it's expected you will consider the weight force as one of the forces acting on the body. Weight force is mass times gravitation acceleration. I hope this hint helps you attempt exercise 8.
For the answers shown here, this is the maximum force in the rod. That's when the object is at the lowest point of travel. And this is the minimum force in the rod. That's when the object is at the highest point of travel. So a quite thought-provoking question, but I'd encourage you to attempt that. The key is to draw the free body diagrams and include all the forces. Don't forget we're considering D'Alembert's principle here, so you will include the centrifugal force in your balance and you will summate all the forces to equal to 0. And question 9 is similar to what we've analysed before. I'll let you review that at your own pace. Answer is shown in the bracket. I would encourage you to stop the presentation and attempt these 3 questions, but I'll show you the full work solutions on the following slides. Question 7, here's the full solution. Nothing particularly unusual about this question. Just be careful of converting the mass from 60 grams into kilograms. I'll let you review the solution at your own pace. Here's question 8, start of the solution here. In this particular case we have an object or a body of mass 3000 grams, so m is 3 kilograms. It's located at the end of a rod that's whirled around in a vertical circle of 1 meter radius. So the rod length or the radius of our rotation r is 1 meter. We've got to calculate the maximum and the minimum tensions induced in the rod when the object rotates at 180 rpm. So my omega converted from revs per minute into radians per second shown here. So 2 parts of the question. We need to consider the situation. Where would the maximum minimum tensions occur? Well, if you think about it, the maximum tension occurs at the bottom of the travel, the lowest point in the travel, and the minimum tension occurs at the height of the travel. But we'll see that from the free body diagrams shown on the following slides. So question 8, solution continued here. So let's consider part A. This will be the maximum tension. This is when the mass or the object is at the lowest point of travel, at the bottom of the travel, so down here. If we draw a free body diagram of the mass for its lowest position, then we will obviously have a centripetal force acting inwards. We have to have a force that acts inwards here to provide the circular motion. Because we're applying D'Alembert's principle, we will have a centrifugal force acting out. We will also have a weight force that always acts vertically down. So that's our static balance in this particular case for the mass at the lowest point of travel here. Because we're applying D'Alembert's principle here and we're considering force in the vertical sense, so vertical equilibrium can be considered when we add up all the vertical forces, they must equal to 0. Notice that upward forces are positive here. So, considering my free body diagram over here, the force in the rod is positive, but the centrifugal force and the weight force are negative in this particular case. All I do now is rearrange the equation to find the force in the rod. So that's simply going to be the centrifugal force and the weight force. We know centrifugal force is m omega squared r, and we also know that weight force is mg, mass times gravitational acceleration. So inserting the values and noting that the radius is actually 1 in this particular case, and gravitational acceleration is always assumed to be 9.81 meters per second squared, we can evaluate the force in the rod as 1095 newtons. That's the maximum force you'll see required to give the circular motion. Question 8 continued. Part B here, we're now considering the situation where the mass is at the top of the travel, and this will be the minimum tension when the mass is at the top of the travel. Again, same procedure, drawing a free body diagram on the right hand side here of all the forces acting on the mass when it's at this position here. So the centrifugal force will act outwards or upwards in this particular case. The force in the rod will act downwards at this point here. The weight force always acts downwards. So this is our static balance for equilibrium here. So for vertical equilibrium here, summating the vertical forces, they must equal to 0. And again, upwards forces are positive. So this time I see my centrifugal force is positive. My force in the rod is negative. And my weight force is again negative. Rearranging to find the force in the rod, that's the centrifugal force minus the weight force. In this case, my solution is just slightly different here. I've actually factorized this time on the m values, the mass values common to both terms here on the right hand side. So I've actually factorized this. In part A I didn't, I just evaluated the two separate terms, but here I've factorized and then inserted all the values here. So this time the force in the rod is approximately 1037 newtons, and that's the minimum force in the rod. I would encourage you to start the presentation, just think through carefully parts A and B solutions here. They're slightly more complicated than the solutions we've seen in previous questions. So again, the key to the problem is first of all drawing a free body diagram of our situation, inserting the centrifugal force because we're applying D'Alembert's principle, and then solving for the unknown force in the rod using static equilibrium. Question 9, here's the solution. I'll let you review this at your own pace. A little bit of transposition will be required in this case. Got to find the radius of the circle for the given parameter, so finding r in this case. Question 10, question 11 and question 12. I will let you review these at your own pace and extract the information as required. I would encourage you to stop the presentation and attempt these questions, but the answers are shown in the brackets on the right hand side. I will show the full solutions to question 11 and question 12 on the following slides for your reference. Here's the solution to question 11. Be careful with the information given in the question. The question wants us to find the greatest speed, the nearest kilometre per hour, that a car can traverse a humpback bridge without the wheels leaving the surface. We're given the radius of curvature of the bridge, it's 10 metres, and we're given the centre of gravity of the car, that's 980 millimetres above the road surface. So be careful with the information, and we're given the centre of gravity of the car, it's 980 millimetres above the ground. So radius of curvature of the bridge, 10 metres, height of the CG above the ground, 0.98 metres. So we're applying D'Alembert's principle as always with these problems, using the body fixed axis effectively on the car. Just note that at the maximum speed at which the vehicle travels over the bridge, the limiting conditions is given by the centrifugal force equal and opposite to the weight force. And so there's no reaction from the bridge on the tyres. Question 11 continued. Here's the free body diagram shown here. So notice the actual radius of curvature in this case will be 10.98 metres. That's the radius of the bridge added to the height of the CG of the car above the bridge. And on my free body diagram, I've got the weight force acting down, balancing the centrifugal force acting up. Because this is a static equilibrium condition, we simply equate the forces. So my upwards force is the centrifugal force, the mv squared upon r. I'm trying to find the linear velocity, so I'm using v in the formula. And that equates to the mass times gravity for the weight force acting down. Just simply rearrange the equation now to find v as a subject. It works out to be the square root of gr, because the masses cancel here, so they do not appear in the final equation. Inserting the values, v is equal to 10.38 metres per second, or converting to kilometres an hour, 37.4 kilometres an hour. So we would suggest that the speed should not exceed 37 kilometers an hour. Here's question 12, solution. In this question, a turntable rotates at an angular velocity of 19 revs per minute. We're given that the coefficient of friction between the turntable and the body that rests on it is 0.5. We're asked to find the greatest possible distance of the body from the center of rotation. So in this particular question, it's the frictional force, usually we denote as FF in our calculations, that provides the centripetal force, the inward force causing the motion. We know from our previous lecture that friction force is equal to mu n, where mu is the coefficient of friction, that's given in the question as 0.5, and n is the normal force, which is mass of the body times gravitational acceleration, which we assume to be 9.81 meters per second squared. What essentially will happen here in our process is it will generate two equations, one based on the friction force and applying D'Alembert's principle, one based on the centrifugal force, the outward force. And we'll solve these equations simultaneously. And here's the full work solution for question 12. To extract the information from the question, the turntable rotates at an angular velocity of 19 revs per minute. So we've calculated the angular velocity omega here. 19 revs per minute equates to 1.9897 radians per second. The coefficient of friction between the turntable and the body is 0.5, so mu 0.5. We said previously the friction force FF is mu n, and on our free body diagram here, there's the friction force, that's the inward seeking force on our mass or on our body. This is a plan view, and this is a side view showing the friction force. We know that the normal force N is m times g from our previous work, so we can write the frictional force as mu mg, and I've called that equation 1 for reference. And then the outward force, the centrifugal force, shown here on our free body diagram, will be equal and opposite to the frictional force for equilibrium. Don't forget we're applying D'Alembert's principle here. So the centrifugal force is m omega squared r, and I've called that equation 2. Because we are now analysing a static situation, we apply Newton's first law, summate all the forces, they must equal to 0. Another way of expressing Newton's first law in this case is to just equate equations 1 and 2. So that's what we're going to do here. Equate the equations 1, which is the frictional force, to equation 2, which is the centrifugal force. We can note straight away that the mass cancels on either side of the equation, so the equation simplifies to mu g is equal to omega squared r. The question wants us to find the greatest distance that the body can be positioned from the centre of rotation, so we're trying to find r in this case. So rearranging the above equation for r, we simply divide both sides by the omega squared term. So inserting the values for mu, g and the omega squared, angular velocity squared, the maximum radius is 1.24 meters to 2 decimal places. I'll leave you with two further questions. Question 13 is another turntable type problem, but this time we have to determine the coefficient of friction. And question 14, another turntable problem, but this time you have to calculate the angular speed of the turntable. The answers are shown in the brackets. I'll leave you with those questions to solve at your own pace. Here's the bibliography used to help generate this presentation, and I hope it's been of use to you, and thank you for viewing.